Thank you for being with us today. Happy to see you all here for this talk, which is part of the CIS Get to Know Your Neighbor Seminar Series. As you know, with the seminars, we strive to provide a platform of cross-school exchange for our EPFL community. Last month, we had the pleasure of hosting Professor David Thuyer from ENAC. Today, we are delighted to have Professor Jürg Schiffmann, the head of the Laboratory for Applied Mechanical Design, with us, who is going to give us a talk entitled Steps Toward Automated Design. To give you an idea of what to expect, I think we all know the format by now. The seminar will last for approximately 1 hour, with Jürg presenting for 40-45 minutes. We will then have 15 to 20 minutes of Q&A. Please post your questions in the chat. This will help us to collect them for discussion during the Q&A session, during which you will also have the opportunity to unmute yourself to ask them directly to Jürg. Before we dive into the presentation, I would like to thank, of course, Jürg for his availability and the entire CIS team for organizing this event this afternoon. Jürg, the screen is all yours.
Thanks a lot. Thanks for the kind introduction, Jan, and welcome to all of you this afternoon to this seminar. So before starting, let me acknowledge Cyril Pica, who is a PhD student of mine. He's just in the process of wrapping up his PhD thesis, and I'm acknowledging him because I've borrowed a couple of results and also some slides from him for this presentation. So let me start straight away into the motivation for the research that we're currently undertaking in my laboratory, the Laboratory for Applied Mechanical Design within the Department of Mechanical Engineering. So fact is, we're consuming too much energy. We're consuming too much fossil fuels. The red curve here is showing the yearly CO2 emissions as a function of the years for the reference scenario, which basically means we go on and burn fossil fuels as if nothing happened. And there is a clear increase in trend, which raises, of course, the CO2 concentration in the atmosphere with known consequences. Now, the International Energy Agency has come up with the so-called 450 scenario, which is the represented by the green line here. It's called 450 scenario because it limits the concentration of CO2 in the atmosphere to 450 ppm, which is thought to limit the increase in temperature of the atmosphere, to limit it down to 2 Kelvin. Now, what we have to do to reach that scenario is, of course, to increase the share of renewable energy vectors. Biofuels for the transportation and nuclear power plants have a role to play, although we're phasing them out. And of course, carbon capture and sequestration to limit the emissions of CO2. However, what this graph shows is that 50% of the required cuts can actually be achieved by increasing the conversion efficiency, mainly at the user end efficiency. And this is exactly where we as a lab would like to contribute to our society with engineering, with research, and also with methods to come up with solutions that are significantly more efficient than they are currently. Now, if you have a closer look at where the energy comes from and where it goes, we can actually see that 27% of the primary energy consumption worldwide goes into domestic heating and air conditioning. So considering this is a region where, or at least a sector where with relatively little effort, a lot of impact can be gained. So let me explain this by this very simple graph. Most of the domestic houses or the households in Switzerland are being heated by a fuel boiler. So if you consider a house that needs 100 energy units to be kept warm, you need to invest approximately 105 units of fuel so that you keep your house warm. Okay, so this means that you are ending up with an energy ratio between what you get over what you invest of 100 over 105. Okay. Now, if rather than burning that fuel in a fuel burner at your home, you burn it in a thermal power plant, a centralized power plant, a modern one here with about 60% efficiency, you feed the electricity into grid, you take the electricity from the grid and drive a heat pump, well, then that energy ratio looks completely different. It basically allows to cut down the energy consumption, the primary energy consumption, and also the CO2 emissions by nearly 50%. This is just simply changing the technological combinations that you're using for heating. Now, if we consider the performance metric of heat pumps, which is basically measured as the ratio between the heat that you're getting over the electrical energy that you use to drive this heat pump, this factor has been increasing in the early 90s and then has, sort of been stagnating over the last couple of years. Now, this rise in the coefficient of performance, and these are actually all measurements coming from the Swiss Heat Pump Test Center, which is a certification unit where heat pump manufacturers can certify their heat pumps. Well, this trend here shows that in the early 90s, there has been a rise of the coefficient of performance by the introduction of a new type of compressor. Now, the key question, of course, is, can another step change like this one here be achieved? And if so, how can this be achieved? Now, in order to answer this question, we have assessed the energy losses in typical heat pumps. And it turns out that 50% of the overall losses in heat pumps are generated in the compression process. 30% are happening during the expansion process and 20% occur during the heat transfer. Now, what are possible ways to reduce these losses? Well, of course, one can directly work on increasing the compressor efficiency. One can go towards what is called oil-free compressor technology, because the oil that is used in positive displacement machines, so imagine a piston machine, it requires oil, first of all, to lubricate the sliding parts, and is also used for sealing. Now, that oil is going out into this heat pump cycle, is contaminating the surfaces of the heat exchangers and is depreciating the heat transfer coefficient in these heat exchangers, which increase the losses. Okay. Another way of increasing the performance of heat pumps is to go towards multi-stage cycles, where the expansion and also the compression is split into several stages, with, from a thermodynamical point of view, is improving the performance. Now, the challenge is that increasing the compressor performance of existing compressors is very difficult, because these machines have achieved maturity. So they have achieved sort of their peak efficiencies that they can gain. You can only gain an additional peak in efficiency by investing a lot of money and making these machines much more expensive. Then the implementation of multi-stage cycles is complicated if you have oil migrating within the loop, because you have to make sure that the oil that gets out of the compressor also gets back to the compressor to avoid it from running dry. So if you have multiple stages with this open flash tank here, this economizer here, it is very challenging to make sure that both compressors still see sufficient oil. So you need to add an additional oil management system. So a potential enabler to tackle all of these three ways to reduce the losses in heat pumps is to change the compressor technology and going away from positive displacement machines towards turbocompressors, and ideally have the turbocompressors on oil-free bearings. So turbocompressors are actually known to achieve very high efficiencies. So this is why we have decided, okay, let's design a small-scale turbocompressor for driving domestic-scale heat pumps on oil-free bearings, so that we can improve heat pumps significantly compared to what is currently existing on the market. So the design task was to design a turbocompressor on oil-free bearings. Now, the typical design process that we're going through when we have some specifications or some customer wishes, that design process is divided into 4 phases. And the design process starts with a problem definition, where we basically nail down the specifications of what the customer really wants. So it's basically making sure that we write down on paper all the numbers related to the customer wishes. Then we go into what is called the conceptual design. This is where the design team puts together different working principles, physical phenomena to achieve what the customer would like to achieve. Then we go into the embodiment phase. This is where we take the concept and start putting geometrical sizes, where we start defining power levels, etc. And ultimately, we go into the detailed design phase where we solve and finalize the nitty-gritty details before we can actually manufacture this design. Now, as you can already hear out, is that the problem definition is sort of the initial phase and the only phase where we have a true customer interaction. This is where we talk to our customers, interview them, and make sure that we understand the problem at hand. Okay, and here we define the specs, and we define the specs for this heat pump compressor as follows. So we wanted to design this compressor for domestic scale heat pump. So it's a heat pump that needs to deliver approximately 10 kilowatts of heating power. Defining or specifying the working fluid inside this heat pump. This allows to define the range of mass flows that this compressor needs to be able to achieve, inlet pressures, inlet temperatures, but also the pressure ratio that this machine needs to be able to deliver. And also, in discussion with compressor manufacturers, we identified what is the expected lifetime of such a machine. And what is interesting is that these compressors actually need to achieve a lifetime of approximately 150,000 hours without maintenance. Now, this doesn't seem quite a lot, but if you compare it, for instance, to your car, which has a lifetime of about 3,000 to 4,000 hours, this is a factor 40. And your car, every 500 hours, you bring it to the garage and you change the oil, and people in the garage are changing parts without you knowing. So the 150,000 hours of lifetime is actually quite a lot, especially without maintenance. So bearing that in mind, we then went into what is called the conceptual design. So in the conceptual design, based on the specifications, we identified, okay, we're going to need a centrifugal compressor over an axial compressor to achieve the high pressure ratios that are required, fitting also the mass flow ranges that we need to achieve. Considering the power levels that we were tackling, we identified, using best engineering practices, that this machine needs to rotate at speeds in the order of 200,000 evolutions per minute, plus minus 10, 20%. And this, of course, immediately has been raising the question about what kind of bearings are we going to use. Because rolling element bearings, such as the ones you see here, is the first choice for a mechanical engineer. It's a very robust system. You can select it in catalogs, etc. However, for these rotor speeds and these lifetimes, that is a pair that really doesn't match for these bearings, because the inertial forces generated by the rolling elements here are actually wearing out these bearings very fast, especially at high rotor speed. So in these rotor speeds, for these power levels, rolling element bearings, if they're well designed, they might achieve 200 hours of lifetime. Okay, and then they need oil or grease to lubricate, so it's a no-go. So the other technology that remains, which would be a feasible one, would be magnetic bearings, but then they are expensive and also cumbersome, so they make the system rather big and bulky. And the alternative would then be gas-lubricated bearings, where we would use the process gas in the compressor directly as a lubricant for these high-speed rotors. In the embodiment phase, we then started, putting numbers on the geometry of the motor, of the bearings. We sort of investigated different rotor layouts. So which ones are the ones that are easily manufacturable, which ones are the more expensive ones, where can problems occur. And this is where you start converging already towards a solution. You start knowing about the size of your machine. But still everything is quite, is not well defined yet. It's the high degree of definition then is only started when you go into the detailed design, where you start using high fidelity models such as finite elements or computational fluid dynamics to design the aerodynamics of the impellers and the bearings. Ultimately, you end up with manufacturing drawings, which you can then send to the workshops to manufacture your prototype. I think you can already figure out that hearing me talking about the embodiment and the detailed design these phases are not necessarily sequential. They are rather working together in iterative loops, right? So when you go into the detailed design, it might turn out that a rotor layout that you have selected or a bearing design that you have selected does not necessarily meet your expectations. So you go back to the embodiment design and then go into a detailed design phase again. And that process being iterative is very challenging. It's very challenging in particular if you don't necessarily have the experience or the knowledge about how these machines would actually work. So actually designing a very small scale turbocompressor was sort of the first time this was done for these kind of applications. So we had no best engineering practices to tackle that problem, which means that the iteration loop between the embodiment and the detailed design was quite a tedious one. It was a tedious one because we used high fidelity models, which takes a lot of time to get the results, and you iterate. So that process is a really lengthy one. In addition, you as an engineer, in addition to make this machine feasible and operational, you also want to make it optimum, right? And if you do this iterative process manually on your own, then you're actually never really sure whether the machine you're designing is an optimum one or not. So you're never achieving peace of mind. And this is a very challenging problem for a design team, okay? Yet, at some point, we decided we step out of this design phase, we manufacture it, we assemble it, we tested it. What came out is this 20 millimeter tip diameter compressor. It has been running up to 210,000 revolutions per minute, pulling a power of 2 kilowatts, reaching pressure ratios of 3.3. The machine is fully oil-free, so the gas-lubricated bearings are lubricated with the fluid that is processed by the compressor itself. And in the picture that you see here on the right-hand side, you see the comparison between the turbocompressor here and the classical machine. Both machines can drive exactly the same heat pump. And as you can see, it's oil-free and it has an increased specific power by 1 order of magnitude, which is very interesting also for transportation applications. When comparing this turbocompressor from a point of view of isentropic efficiency over the pressure ratio and comparing it to a classical state-of-the-art positive displacement machine, you can see that this turbocompressor achieves higher efficiency than positive displacement machine, and it also improves the off-design performance, which for a heat pump is actually key to achieve high performance. So if we go back to the initial question whether there can be another step change in increasing the coefficient of performance of heat pumps, well, the answer is yes, it can be achieved. It can be achieved by implementing multi-stage heat pump cycles that are driven by oil-free turbocompressors supported on gas-lubricated bearings. The increase of the coefficient of performance compared to what exists on the market currently is a plus of 25% with this technology. Now, having developed this turbocompressor, shown that a very small scale turbo machinery is actually feasible, that it can achieve high efficiency, there has been a snowball effect, which basically meant that we have designed other gas lubricated high-speed shafts with turbines for turbo expanders for truck waste heat recovery that allows to reduce the fuel consumption and also CO2 emissions by a considerable amount by recovering heat from the exhaust gases of these truck engines. Another project which I'm quite proud of is this project here, where we have designed a very small scale anode of gas fan for recirculating anode of gas from a solid oxide fuel cell. This machine is not driven by an electrical motor, but rather by a steam turbine, where the steam is actually produced by the waste heat of the solid oxide fuel cell. The beauty is that this is a 6 kilowatt class solid oxide fuel cell, so it's domestic scale, and we have achieved 60% efficiency in the lab at these power levels, which is actually 4 points more than the world record of a combined power plant that generates 1 gigawatt. But this is 1 gigawatt centralized power where you need to distribute it, right? So you have distribution losses. And here we achieve 66% in your cellar. So this is quite an achievement. And I think these three examples together with the heat pump show that small scale and also turbomachinery is an enabling technology towards improving the energy conversion efficiency, and is sort of a brick, an interesting brick towards a path towards a more sustainable energy landscape. Now, if we go back to design challenges that are related to this high-speed turbomachinery, if we try to characterize the design problem itself, we actually see that it's characterized by a very pronounced multidisciplinarity, right? So we have to design the aerodynamics of turbomachinery. There's gas-lubricated bearings, there's rotordynamics, there's an electric motor, there is the electronic drive to drive this high-speed electric motor, there's the whole thermal management, and last but not least, there's the whole design process to get towards an ideal design of this machine. So there's many disciplines coming together that one design team has to tackle to achieve an operational prototype, or even industrialize this in a product. This is also characterized by strong interactions between the different components. Designing the turbocompressor has a direct impact on how much thrust forces are generated, and these thrust forces translate in a truss bearing that needs to be able to cope with these thrust forces. Now, this truss bearing generates losses. These losses affect thermal management. The thermal management affects the behavior of the journal bearings. So, everything is in the loop. So it's a very complicated problem to design with, especially if you're doing the optimization manually and on your own. In addition, and this is common to all mechanical design problems, they're characterized by competing design objectives. So on one hand, you want to maximize efficiency, but you also want to make it as cheap as possible, right? So these are typical competing design objectives. And in addition, they're characterized by a high level of design constraints, meaning that your machine has to be optimum, but in addition to that, it has to be feasible. So think of the mechanical stresses. The mechanical stresses limit the solution space within which you can actually search for solutions. The machine needs to run in a stable manner on these gas-lubricated bearings, which are prone to instability. So all of these are design constraints which limit the solution space and which make it really complicated at times to even find feasible solutions. Now, the traditional approach, or the classical, the straightforward approach to tackling complex design problems as this one is actually to split the complex design problem into different digestible chunks, okay? So the idea is basically you sort of predefine a layout of your machine, a conceptual layout, an embodiment, and then you split everything up into digestible chunks. You give the turbomachinery expert the task to design a compressor that fits this embodiment, same for the bearings, same for the rotordynamics, same for the electric drive and motor. And then you as a project manager hope that everybody does his best to get the best parts. You put them together and hope it actually works. This is is a totally valid approach, but it tends to neglect component interactions. And by doing so, we hypothesize that it yields suboptimal solutions because the sum of optimum components is not necessarily the overall optimum of your design. It's also a hindrance to novel solutions because if you have to design specifications for the bearings and for the aerodynamics, you already need to have an idea of where your design is going, right? So you need to get inspiration from what has been done previously by your colleagues. So it's a hindrance towards novel solutions. And last but not least, it's a solution that doesn't offer peace of mind to the design team because you are in this manual optimization loop where you try to maximize and to do your best, but you're actually never sure that you are there. You're never sure that you have achieved the maximum efficiency, and that can be a problem. Now, the way how we tackle that is rather than doing this optimization manually, we have formulated the design problem as a multi-objective optimization, where we basically define objective functions. Here, it's basically maximizing the efficiency and maximizing a rotordynamic performance metrics where both of these functions are dependent on G, where G is design variables that fully describe the bearing, the rotor, the motor, and the impeller geometries. And for every one of these geometrical sets, we calculate these performance metrics, and we feed that function to a multi-objective optimization algorithm that is, of course, subject to certain constraints that make sure that the solution is feasible from a manufacturing point of view, the bearings generate sufficient load capacity, and that the mechanical stresses, are within the limits of the selected materials. Now, after a very long computation on a high performance cluster, this is the red dots here are basically the Pareto curve, which identify the ideal trade-off between these two design objectives that we want to achieve. So maximum system performance and maximum rotor dynamic performance. So you would like to have solutions in this upper right corner here. And what this curve shows, and the interesting part is actually the yellow star here. The yellow star is the proof of concept compressor that we have designed by optimizing the whole system manually. So basically, we optimized the aerodynamics individually of the compressor, the bearings individually, etc., and put it all together and tested it, right? This has actually also served as a means to validate our reduced order models that we then used for this optimization. But what this curve basically shows is that keeping the same rotor dynamic performance, you can actually improve the system performance, the efficiency of the machine by 12 points. And if you compare the proof of concept solution with the optimum solutions at the same rotor dynamic performance, the difference is not so flagrant, right? The bearings are slightly smaller, the motor is slightly more elongated. What you don't see on this picture here is that the compressor is running at slightly lower speed, which is depreciating slightly the performance, the aerodynamic performance of the compressor, but by running slower, you can make the rotor slightly elongated, which is reducing the windage losses. Now, this is the typical trade-offs that by doing a manual optimization in a fragmented approach, you would not detect. And I mean, 12 points of efficiency increase is significant, right? And this certainly validates this integrated design and optimization approach. Now, a challenge here is that finding this Pareto curve is very time consuming because, first of all, our models, they're reduced order models, but they're still computationally expensive. It's the way of how we did the optimization and the constraint handling is suboptimum. So there's still a lot of work to do. And another challenge is that it turns out that solutions that are on this Pareto curve are not necessarily very robust towards manufacturing deviation. So it means that if you have some manufacturing deviation of this optimum solution here, it might fall into a non-feasible region or the efficiency might drop significantly. So there is clearly, additional things that we need to add to this integrated design and optimization framework, notably the robustness. However, the robustness or assessing a robustness for manufacturing deviation is very challenging because the response surface of these performance metrics is a highly non-convex surface. So this means that gradient-based approaches cannot be used. So we need to have a very high sampling rate around these nominal design points to assess the performance of that machine, which adds a lot of additional computational points, which means that with the current models, this is computationally prohibitive. So this is why we're looking into surrogate model approaches. So we're using artificial neural networks to model the compressor, but also the bearings, so that we can actually speed up the computation of these models. So we have had promising, very promising results for modeling the aerodynamics of the compressors, which compared to our reduced order model, the artificial neural networks are 6 orders of magnitude faster, which is actually, really interesting when it comes to these integrated design and optimization approaches. Now, before wrapping up, I would like just to briefly discuss about another application where we have applied this integrated design approach to a very concrete design problem in industry. the design problem that we have that I have shown now is gas bearing supported turbocompressor is not necessarily something that exists on the market. So this is something really novel. On the other hand, we have been, and this was basically an Inno-Swiss project together with a company in Switzerland, of course, where the company is manufacturing electromechanical actuators for the car industry. Electromechanical actuators in the cars are ubiquitous, so they're used for the the ventilation flaps. They're used for adjusting the height of the lights. They're used for the grille shutters for the optimum thermal management of your engine. There's even parking brake actuators for the electronic parking brakes, etc. Common to all of these actuators is that there is a motor. The motor is followed by a gearbox with several stages of gears. There is an output, and the output is specified by a certain torque that needs to be applied and a certain speed that needs to be achieved. In addition to that, that actuator, and this is a very stringent constraint, this actuator needs to fit into a very specific box. Okay, so from an engineering perspective, this is a very easy design problem, right? It's basically sizing an electric motor, sizing gears. This has been done for decades. It's an easy design problem. However, if we're coming back to this design process, we clearly see that, okay, there's a problem definition where specifications are exchanged with the customer, but it's primarily a design problem that emphasizes on the embodiment and detailed design phase, okay? And this is a very routine task where, in essence, one project manager and two specialists are working for approximately 1 month using Excel calculation spreadsheets to size the gears, to identify how many gear stages, to design the motor, and most of all, to do the packaging so that this gearbox fits into a very detailed box. Okay. The challenge is that when the customer comes to this company, they give the specifications and they say, we want this actuator, give us the best price. So the design team is working for 1 month approximately for free, right? Because they don't have the contract yet. And when they come up with the price, they're in competition with other companies. So there's not necessarily certain that they will have the contract to produce how many dozens of millions of these actuators. So it's a lot of investment before they actually get the contract. So this company came to us and told us, can you help us in speeding up that process? So again, well, this is a repetitive and very tedious piece of work. Also, the engineers agree on this. Now, Cyril, so the PhD student, has actually made an integrated actuator model where that basically captures the key physical phenomena of the electric motor, of the gearbox, of the gear pairs, and is also able to predict the cost of these actuators. In addition to that, and this was a little bit of a challenging part, is we wanted to be able, to identify the ease of assembly, collisions, internal collisions between shaft and gears, but also collisions with a bounding box of your actuator. And he has implemented techniques that he has taken from the gaming industry to have a really integrated actuator model that allows to predict the performance, the cost, but also identifying a potential violation of constraints. And then he has implemented this into a web-based tool, where basically the problem is conditioned numerically. This whole problem is then fed into this integrated actuator model together with a multi-objective optimization, the evolutionary algorithms. He has worked on constraint handling methodologies, if you're interested by this, to speeding up the convergence of these optimization processes. And then the final results basically come out as a Pareto curve, where the engineers can make an informed decision together with the customers about where they would like to place their actuator, how it looks like, what materials are being selected, how it's being packaged, and how much it costs. Okay. Now let me show you an example. The example that you see here, and the example that you see here is an actuator that has been optimized for ventilation flaps in cars. What we optimized was maximizing the torque. So here measured as a torque excess. So a zero torque excess means that we meet the customer specifications and we wanted to minimize cost. Okay, and we did this optimization for 3, 4, and 5 gear stages. And we did this optimization, you know, on a laptop computer. And what can clearly be seen is that the green square that is circled on the far right of this graph is the model, is the design that the company came up after 1 month of work. Okay, and these curves here, they have been achieved on a classical laptop within 2 hours. So I think this clearly shows that this, you know, integrated approach has an automated design. So it's basically an automated, or part of the design is being automated here, has a very clear benefit. It has a benefit because it avoids a very tedious part of the job of the engineers. It also helps because it's so fast that the salesman can actually go with the laptop to the customer, discuss specifications, you type in the specifications, you let the optimizer run, you take a coffee, talk about other things, and then you have the Pareto curve on your screen. So you can basically have the customer that is part of your design process from the beginning nearly to the end, right? Because the customer might actually see, okay, you know, you're right, I don't necessarily need that much torque. I can also live with a little bit less torque, right? So you can directly identify how much the actuator is getting cheaper by doing so. Okay, so let me wrap up. What is the outlook and what are the next steps that we're planning? Of course, we want to push the design automation towards earlier phases of the design process. So up to now, we are working on the detailed design phase. We're pushing towards the embodiment, but we're clearly not there. So the idea is to push even, you know, towards earlier phases of the process. It's not clear to me how far we can push this exercise. What has been identified also for this gearbox and electronic actuator problem, the robustness, so the robustness of solutions with regards to manufacturing deviation is a very important topic, because if you can manufacture parts with a large tolerance, this is also decreasing cost. So if you can find a solution that is very robust towards manufacturing deviation in terms of their performance, that is actually very beneficial also for the cost of the system. Now, robustness calls for even faster models. So we are certainly going to work on surrogate modeling techniques. And working on the surrogate modeling techniques has brought us up into another subject, which, you know, has given us some grievance in our lab when we tested our high-speed compressors. There were machines that, you know, would break, would stop out of nowhere. And it's only when we analyzed data at a later point of time that we realized, well, you know, there might actually be precursors that tell us, be careful, your machine might actually work in an anomaly. And you know, if we had a sort of a tool that raises a flag and tells us, be careful, you are running towards an anomaly, we might have saved the prototype. And these prototypes don't come so cheap. Huh? So for a lab like ours, it's expensive parts. So this sort of you know, gave us the idea to work on computationally cheap digital twins for real-time monitoring, which is you know, which is now part of a project that is being financed by the Center for Intelligent Systems. We're in the process of looking at application files, and we're looking forward to start this project very early on. So this is a project that is joined with the lab by Fabio Nobile. So we're looking forward, you know, to collaborate on this. So it's 15:57. I think I'm nearly on time. And then I would be very glad to take your questions if there are any.
Jürg, so then please let me say some words of closing. First of all, thank you, Jürg, also for this great presentation today. Thanks to all of you for the discussion. The next events, just a brief announcement, July 5th, we're looking forward to host Professor John Mannix, head of the Laboratory for Computation and Visualization in Mathematics and Mechanics. This is Get to Know Your Neighbor. And then we will be back in October. There should be a slide on the screen, but it's not showing up, with Pavan from SV, who is going to present his work in life science. Thank you so much. Have a nice afternoon and hope to see you soon again. Take care.
Yep, thanks a lot. Bye-bye.
Bye. Talk soon.